if I go to do this multiplication and I know that my result is going to be a 2 by 1, that means in my first row, first column, I need to multiply the first row by that first column. Happens to be our only column. So I'm going to write this out and then clean it up. So -6 times 4, that's going to be -24 plus 4 times 3 gives me 12. -3 times 4, that's a -12. Plus 1 times 3 is 3. And if I clean that up a little bit, I think I've given us pretty nice numbers. And I'm going to end up with -12 and -9. I was really strategic about the vector that I gave us. But let's just do one more here. And I'll do this one. So -4, 4, -3, 1. And pick a number between 1 and 10. And give me another number between 1 and 10. 3. So if I do this multiplication, again, just getting our practice back up to speed in terms of doing the matrix multiplication, because it's going to be really important for us in this next section. So -6 times 9, make sure I don't mess up the arithmetic here. That should be 54. Sorry, -54. So I would have -54 and then 4 times 3, so plus a 12. And down here, -3 times 9, that's going to be -27. And plus a 1 times 3. So if I clean that up over here, -27 plus 3 sounds like I'm at -24. And -54 plus 12 sounds like I'm at -48. No, 42. Thank you. See, I told you I needed you to help me not mess up this morning. Okay. So we haven't talked much about this. We touched on it just a little bit in 19B, but in general, if I multiply a matrix times a vector, I'm just getting some other new vector out. If I think about that matrix as some sort of linear transformation, then it's taking this vector and shifting it to be this vector. Applying this matrix transformation to this vector shifts it to be this vector. Well, it turns out that sometimes for very special vectors, that shift doesn't change the direction of the vector. It only changes the magnitude of the vector. And when that happens, we call that vector an eigenvector. So here, this one, if I think about the vector 4, 3 and the vector -12, 9, those both live on the same line in space. So if I think about that vector 4, 3 graphically, I can think about starting at the origin. I'm going 4 to the right and up 3. So it's kind of going through this coordinate 4, 3. Which means that that lives on a line with a slope of rise over run. So that's got a slope of 3/4. And if I think about this other vector, the -12, -9, so that says I'm going out -12 in this direction and then down 9. So that's at the coordinate -12, -9. And these are actually on the same line. So if I were to think about the slope for this point, I'm rise over run. So I rise 9 and move over 12. So that slope is 9/12, which reduces to 3/4. So when we have this special thing happen, we call that vector an eigenvector, and the eigenvalue is essentially how that vector got rescaled. Fundamentally, that relationship between an eigenvector and an eigenvalue is going to look like I have my matrix, and when I multiply by the eigenvector, if what I get back is a scalar times that very same vector, then I call that scalar the eigenvalue, and we call that vector the eigenvector. So for the example that I just did, our matrix was -6, 4, -3, 1. We multiplied by that eigenvector for 3. What was the scalar if we ended up with the vector -12, -9? So this would be my eigenvalue. And the associated eigenvector is 4, 3. So we've been working with differential equations, and now out of nowhere, we've popped back into linear algebra. And what we're about to do is to tie those two things together. So just as a quick, this will be, we could treat this as review for the midterm. But if I have a differential equation that looks like dy dt is equal to a scalar times y, where that is a constant, can we solve that differential equation? What kind of differential equation is this if I had to apply some vocabulary? It's autonomous. And it's also separable. And since it's separable, we can solve this. So I'm just really quickly going to solve this thing. So I can divide both sides by y, multiply both sides by dt. This one's pretty straightforward, so I'm just going to do this for ourselves. What do I get when I take the integral of 1 over y? So I've got ln absolute value of y. Here, because I made it with respect to time, I would have lambda t plus some constant. And then to get the y by itself, I'm going to have e to the lambda t plus a constant. And then we're going to do that trick to handle, since technically that's absolute value, we're going to do our trick over here and think about that as e to the lambda t times e to the c1 and just relabel that. So y equals ce to the lambda t. So it turns out that if I have a system of differential equations, and I can write that system of differential equations, the system of linear differential equations in a matrix form, then having something that looks like a derivative of y is equal to lambda times y. If this is written in as a matrix, then knowing what the eigenvalues and eigenvectors are allows us to quickly solve the system of differential equations because it's going to be of this form. Thinking back to 19b for a second, we got some practice solving equations that looked like a matrix times a vector equals another vector. And we had a couple options for solving that. One option was that we were going to create an augmented matrix and get it in row reduced form. And the other option that was introduced was to multiply by an inverse. So if I think about this, and if A is invertible, then I can find that vector x by applying A inverse on the left-hand side of both equations. We're just going to keep that in mind for a second. So if I come over here, I can't, even if I had A inverse to multiply on both sides, I would still have this vector V on both sides. So kind of first step of solving this is that I kind of want to get all my V's to one side. So if I do that, I'd have A times the vector minus lambda times the vector. And if I've subtracted this from both sides, what's left? Totally. Now, just like if I pretend that I'm solving this equation and like V is the thing I'm solving for, I can factor out a V right now. There's a little bit of a challenge factoring out a V. So remember, A is a matrix. I'm subtracting a constant. I've got to be careful to factor the V out on the right-hand side. And that's because our matrix multiplication is not commutative. The order that we do it in matters. But if this is a 2 by 2 matrix and lambda is just a number, I can't actually perform that subtraction. So we've got to do one little thing here, and I'm going to insert that identity matrix. As a reminder from 19b, that identity matrix for a 2 by 2 looks like 1, 1, 0, looks like 1, 0, 0, 1. And we call it the identity matrix because if I take that identity and I multiply it by a vector, I just get the vector back. So it's kind of like saying we're multiplying by 1. So I'm looking at this and I'm going to rewrite this to think about this part being a matrix M. So I've got a matrix M times a vector, and that's equal to 0. And now I can apply that inverse piece. So I can have my vector is equal to the inverse of that matrix M times 0. What is something times 0? This thing does not have interesting solutions. This equation only has one solution, and that's that my vector had to be 0, 0 if it's a 2 by 2, or 0, 0, 0 if my matrix was a 3 by 3. This solution is boring. In a biological context, this solution means all the critters are dead. If I think about this in an economics, this means I have no revenue because both my sales and both my price and my demand went to 0. This is not the solution we want. We're looking for more interesting solutions. And the only way we're going to find interesting solutions is if this matrix is actually not invertible. So we only have interesting solutions if M is singular or not invertible. Does anyone remember from 19b how we can check if a matrix is invertible? Right. So we only have interesting solutions if the determinant of M is equal to 0. So the way we're going to find interesting solutions is we're going to start by setting the determinant of that M matrix, which came from our original matrix, minus lambda times the identity. We need to set that equal to 0. The first thing that I need to do is kind of to construct that matrix M. So I need to do the A minus lambda I thing. I'm going to write this out the first time, but usually we're going to skip this very next step. So I've got that minus lambda times the identity to construct the matrix. Really, that means that I'm doing 1, 5, 6, 2 minus lambda 0, 0 lambda. So that A minus lambda I matrix looks like 1 minus lambda, 5, 6, 2 minus lambda. It is totally fine to just jump straight here. And I would say after you've done a few problems, you're going to jump straight here. You're not going to write those 2 steps out. So we're looking for the determinant of this matrix and to set that equal to 0. Well, for a 2 by 2 matrix, life works out nicely. And for a 2 by 2 matrix, I go my primary diagonals, AD minus my off diagonals, BC. So I've got 1 minus lambda times 2 minus lambda minus 5 times 6. Set that equal to 0. If it's a 2 by 2 matrix, our result here is going to be some sort of quadratic. So in the best of times, it's going to factor. And in the worst of times, it's going to be complex. I mentioned this at one point in 19B, but here for 19C, we're going to take these eigenvalues, whether they're real or complex. So even if there's a negative under the square root, that's going to be a valid answer for us for 19C. It means something qualitatively different is happening with our graph and with our direction fields and all of that. But we're going to take all the answers, whether I've got positive numbers under that square root or not. Do you all want to practice solving this, or do you want me to actually solve this one? Okay, and just as another pro tip, if you don't like drawing in the lambda, just write it as an X. You'll be fine. If I didn't mess up, this should factor. I'm pretty sure I didn't mess up, and I'm pretty sure it's going to factor. I will get us some practice with ones that don't factor. But okay. Time for me to do some algebra. So if I distribute everything out over here, I am looking at 2. I've got a 1 times a negative lambda, so that's a minus lambda, a minus 2 lambda, a positive lambda squared, and a minus 30. I am stuck in my ways, and I need the lambda squared to be out front for me to factor. So that's going to be lambda squared minus 3 lambda minus 28. And that does look like it factors for me. I need 2 numbers that multiply to be 28. Don't have a lot of options. It's 7 and 4. And I've got to end up with a minus. So I'm looking at lambda minus 7 times lambda plus 4. Ought to do it. So that means that my 2 eigenvalues are 7 and negative 4. Once I know my eigenvalues, I also am going to be able to solve for my eigenvectors. And to solve for those eigenvectors, I've got choices. If you have been reading the new book that we switched over to, the book shows a different method for solving for those eigenvectors than what Dr. Thomas did yesterday. I'm going to stick with the way Dr. Thomas did it yesterday. But if anyone wants to see the way they do it in the textbook, I'm happy to do that also. But I figure let's keep life simple for now. So yesterday in lecture, we saw kind of taking this back to the version where we had our matrix times the eigenvector equal to 0, and then going ahead and writing that out as a system of equations. Reminder that this matrix M is that A minus lambda I matrix already. So that A minus lambda matrix, that A minus lambda I matrix looks like 1 minus lambda, 5, 6, 2 minus lambda. And for my eigenvector, I just need something as a placeholder. So sometimes we like to use subscripts and call it like x1, x sub 2. I'm going to stick with just xy for now because I think our brains work a little bit better that way. So we're going to solve for these eigenvectors one at a time, meaning I'm going to stick in each of my eigenvalues. So I'm going to start by sticking in -4. So if I stick -4 in, then this now looks like, I'll try to be careful here. So I've got 1 minus -4, which is going to give me a 5. Nothing happens to the 5, nothing happens to the 6. 2 minus -4 gives me a 6. So if I write that out instead as a system of equations, that looks like 5x plus 5y equals 0 and 6x plus 6y equals 0. Now you'll notice something interesting happened, maybe. When we do this, if everything has gone well, in almost every case, these two things should simplify to be the same equation. These should tell me one piece of information. Now, thinking back to 19b, if I'm looking for the solution to two linear equations, that means they either intersect at a single point, they don't intersect at all because they're parallel, or they intersect infinitely many times. And the other way to think about that from kind of a visual context is like, if I have free variables, then I know I have infinitely many solutions. And if I were to row reduce this right now, I'm going to end up with a free variable because these two are actually telling me the same thing. So if I took that top equation and I rearranged it to make it say y equals, I could subtract the 5x from both sides, divide both sides by 5, and I would get y is equal to -x. Well, if I do the same thing here, I can subtract the 6x over, divide both sides by 6, and I also get that y is -x. So it turns out that any point on the line, y equals -x, is going to be an eigenvector. And kind of tying that back to that first example that I did, right? Any point on this line would be an eigenvector. So we can choose anything we want, but I will let you know that if you're trying to check, if you're doing problems from the textbook and you're trying to check your answer with the textbook will always choose 1 for x. It actually doesn't matter. Every eigenvector is equally good. I would stick with smaller numbers because if you have to do anything with them, it's just easier to work with smaller numbers. But our textbook will always choose 1 for x. And what that would look like is I could say that the eigenvector that's associated with a lambda of -4, if I set x equal to 1, then y has to be -1. Do you want to go ahead and find the eigenvector that belongs to lambda of 7? So I'm going to set up my determinant of A minus lambda I. So I'm subtracting I'm subtracting lambda from the diagonals. So the nice thing that happens here is that I've got this minus 0, which means it's already factored for us. Now, part of the reason that I wanted to point that out is I don't remember if this ever came up in 19B, but if I already have a triangular matrix, I can find my determinant by just multiplying the diagonals. So even if this matrix were a 3 by 3 matrix, if I gave us the matrix 1, 2, 7, 0, -4, 3, 0, 0, 2, the determinant of this matrix is 1 times -4 times 2, which would also mean that if this was my A minus lambda I, then I would know that my eigenvalues were 1, -4, and 2. And I think it's possible, but I haven't checked, but I think it's possible that the 3 by 3 matrices in the homework are going to have this nice feature to them. We'll find out in a second. That's just my guess, but we'll try some of yours and see if it works out that way. If not, I will show you how to do the determinant of a 3 by 3 matrix.
Wait, what does it mean for the matrix to be triangular? Or like,
oh yeah, so I can have values on the diagonal and anything I want up here, but this corner down here, they're kind of zeros in that bottom corner triangle. So we call that triangular. And when we were talking about row reducing a matrix, our first step was usually to get it into this triangular form. And it just so happens that that triangular form kind of tells us automatically what our eigenvalues are and sort of tells us automatically what our determinant is. So we'll do a 3 by 3 matrix next, but let's finish this off. So I now know that I've got a lambda of 2 and a lambda of 3. So if I start with my lambda of 2, then plugging in 2 for lambda, I would end up with 0, 1, 0, 1. So I've got that times xy is equal to 0, 0. So I'm going to be careful about writing this out. So if I write this out, that top row would say 0x plus y is equal to 0. And the bottom row would say 0x plus y is equal to 0. Well, we got the same thing for both rows. That's good. We should only be seeing one piece of information. Now I claim, and I hope to convince you that this bottom row is telling me that y is equal to 0, but x can have any value. Because if I choose 3 for x, for example, 0 times 3 is 0. That's fine. Plus some more 0 is equal to 0. So I can actually make this equation true for any value of x as long as y is 0. And it's important for us to choose an eigenvector that isn't 0, 0, because 0, 0, right, like my two just things that I keep in my head, 0, 0 in a biology context means all the critters are dead. 0, 0 in an economics standpoint means my revenue is 0, right? Neither of these are what we're looking for. So I don't want to have an eigenvalue of 0. Sorry, I don't want to have an eigenvector of 0. So my eigenvector associated with lambda of 2 could be 1, 0 or 5, 0 or 17, 0. The key is the y value has to work out to be 0. Let's check this out for lambda equal to 3. And then we will visit a 3 by 3 example. So let's say my lambda is equal to 3. Then my matrix becomes 2 minus 3, that's -1, +1, 0, and 3 minus 3 is 0. Well, here, the bottom row is actually not telling us anything interesting at all. So the bottom row, if I wrote it out, would just say 0x plus 0y is equal to 0. Cool. True, not helpful. So I'm just going to focus on the top row this time. So -x plus y is equal to 0. That must mean my x and y values are the same. So my eigenvector associated with a lambda of 3 could look like 1, 1, or 2, 2, or -12, -12. What would it mean for 5 to be an eigenvalue? Well, that would mean that when I take the determinant of A minus lambda I should get 0. So if I subtract 5 from, and as a reminder, for a 3 by 3 matrix, that identity matrix, let me scoot this up here. Determinant of A minus lambda I needs to be equal to 0. So that's my A matrix. And as a reminder, as the size of my matrix grows, the size of my identity matrix grows. So that's my lambda I, and that's my original matrix. So if I plug in 5, what I get from doing A minus lambda I, am I good now? Okay. So when I take the determinant of a 3 by 3 matrix, the way that I like to do this is to expand across a row or a column. And I'm going to choose whatever has the most zeros in it. So would you like to take the last column or the second row? Okay. So I'm going to take the second row. And the way that we're going to find the determinant is I'm going to go through that second. I have no idea. I don't recall you learning this in 19B.
Yeah, so there's two comments. We only learned how to make the inverse, but not to. Yeah.
Right. So I don't know what else to, I don't know what other clever things to do, other than for a 3 by 3. Do we, I'm just trying to help y'all get through the homework. The other option is to just throw this in a matrix calculator and calculate the determinant. If you get 0, then 5 was truly an eigenvalue.
I just don't know how, I just don't know how to.
Yeah, that's why I'm going to show you right now. Okay. So I'm going to choose a row or a column with the most zeros. I'm going to take these the numbers in that row, the 6, the 0, and the 0, and I'm just going to put them over here. I'm going to do something else to them in a second, but I'm just going to, for now, stick them over here. 6 times something plus 0 times something plus 0 times something. Now, the cool thing is the reason that I've chosen a row or a column with zeros is no matter what I put in this matrix, 0 times that is 0. So by choosing something with zeros, I can ignore these two. And I just have to focus on this. That number 6 is in the second row, first column. So I'm giving myself a -1 raised to the rows plus columns. And now I'm going to imagine that I'm blanking out in my matrix both the column that the 6 is in and the row that I was expanding across. And what that leaves me with is this smaller 2 by 2 matrix. And that smaller 2 by 2 matrix looks like 6, 5, 6, 0. And what I'm going to now do is take the determinant of this one. And now that it's a smaller matrix, I'm good to go. So -1 to the third gives me a negative. So I've got -6. And now I can just find that determinant. 6 times 0 minus 5 times 6. It doesn't look like I'm going to get 0 for an answer. So I don't think that that is an eigenvalue of
Is this
my
also-
matrix. Decide for this lovely matrix. So great, loving this so much. Don't know if yours look quite this bad. I've got to show for this matrix is 6, 1, 0 an eigenvector. Now this one, way simpler. This one just requires us to do matrix multiplication. Because this is asking, if I take that matrix and I multiply by 6, 1, 0, the answer that I get, whatever it is, can I make that answer look like a number times the original 6, 1, 0? Now, if you had to do this, which of the three would you start with? Would you start with the first row, the second row, or the third row?
What do you mean?
Well, I mean, I've got to do the matrix multiplication, right? But I'm going to start with the bottom row. Because if I don't get 0, I'm done. If I take the second row or the first row, I have to do, like, I'm going to have to do the first row and the second row if this bottom row is 0. So I'm going to save myself time and check the bottom row first. Because that number, that lambda can't be 0, right? So, well, I guess it could, but I'm going to hope that when I look for the value in the bottom row, it's not 0 and I get to just be done. That's what I'm hoping. So let's find out. So to get this, this is in row 3, column 1. So I'm going to multiply row 3 by column 1. So -5 times 6 plus 7 times 1 plus 31 times 0. That is not 0 and I'm done. This is not an eigenvector. By subtracting off my lambda I matrix. So I know that I'm looking to find the determinant of -1 minus lambda, 0, 0. -2, 10 minus lambda, 2. 7, -40, -8 minus lambda. Now, if that 2 had been a 0, it would already be in triangular form, and I wouldn't have to do much work. I would already know that my eigenvalues were -1, 10, -8. Unfortunately, it's not in that nice triangular form. So we're going to have to do a little bit more work. I'm going to choose the top row because it's got the most zeros in it. So I'm going to take my top row and I'm going to write out my numbers, but I know that those zeros are going to be 0 times something, 0 times something. So I don't have to worry about that. I just really have to worry about that -1 minus lambda. It's in the first row, first column. So I would have -1 to the 1 plus 1, which happens to be positive. I've got that times -1 minus lambda. And then I need to multiply that by the determinant of the 2 by 2 matrix that's going to be left. So I'm going to blank out the top row because that's the one I was expanding across. If I can get a pen to stop rolling. And I'm going to blank out the first column. And I'm going to find the determinant of the remaining 2 by 2 matrix. So that's 10 minus lambda to -40 and -8 minus lambda. So it looks a little bit messy, but it's going to be doable. So -1 to the 2 gives me a positive value there. So I've got -1 minus lambda. So that part's like already factored for us. That's already one of our factors. I know lambda equals -1. And for this part, it's just a regular 2 by 2 now. So I've got 10 minus lambda times -8 minus lambda minus 2 times -40. It might be gross, but at least it's just a 2 by 2.
So it can be.
And then if I multiply this stuff, I'll have a positive lambda squared. I've got a positive 8 and a -10. So that's minus lambda. I've got a -80 and a positive 80. Sweet. This one's super nice. -1 minus lambda. I can factor a lambda out and then I have a lambda minus 1. So mine ended up with really nice eigenvalues. When I set that equal to 0, mine ended up with -1, 0, and 1 as my eigenvalues. I hope yours do too. But for a 3 by 3 matrix, the big takeaway here is if you have a row with a couple zeros in it, you're going to save yourself a bunch of work when it comes to the step of finding the eigenvalues. But I've made it work out nicely. So if I go to find my eigenvalues here, I'm subtracting lambda on the diagonal. And then taking that determinant. So I'm looking for the determinant of negative lambda, 3, -1, negative lambda. When I take that determinant, I end up with lambda squared plus 3. So I gave us something super nice in terms of the complex realm. So when I go to solve for lambda here, I'm going to end up with lambda squared is equal to -3, which up until this point in this entire course, we would have said this thing has no solutions. But now we actually have to write the solutions. So this, once I take the square root of both sides, looks like lambda is equal to plus or minus the square root of 3 times I. And this I right here is the square root of -1.
That is the value of I.
I is equal to the square root of -1. Yeah. And I haven't actually tried to see on the homework. I know there are problems that are asking you about complex eigenvalues. So that one looks like it's going to have complex eigenvalues. Yeah, I definitely have at least one in terms of my numbers that looks like it's gonna have complex eigenvalues. Let's say that the numbers didn't work out quite that nicely.
So is that how we answer in the web course if we have one? with
Yes.
the I?
So just as another quick practice here, so let's say I had 1, -4, 1, 1 as my original matrix. So if I'm trying to find the eigenvalues, I'm going to subtract 1 on the diagonal. So I'm going to have 1 minus lambda times another 1 minus lambda minus 1 times -4. When I multiply that out, I've got lambda squared minus 2 lambda plus 1 plus 4. Or lambda squared minus 2 lambda plus 5. Well, that doesn't factor because my only factors of 5 are 1 and 5. And there's no combination of those that's going to add up to -2. So I know I'm going to need to use quadratic formula. As a refresh our memory, if I have something that looks like ax squared plus bx plus c is equal to 0, quadratic formula says my x is going to be -b plus or minus the square root of b squared minus 4ac all over 2a. And what I've got going on here means that lambda is equal to -b. So it's already -2. So I'm going to switch the sign and make it positive. Plus or minus the square root of b squared. So -2 squared minus 4 times 1 times 5. All over 2 times 1. So that's 2 plus or minus, and now inside my square root, -2 squared gives me a 4, and 4 minus 20 sounds like -16. Whole thing is over 2. Just one like algebra thing to be super careful with. That means both of these pieces are divided by 2. So that's 2 divided by 2 plus or minus plus or minus the square root of -16 over 2. And the way that we handle that square root of a negative, the square root of 16 is just 4. And the way I handle that negative inside is by putting an I there. So that I is my placeholder for the square root of -1. So this is 1 plus or minus 2i would be my eigenvalues.